Now, in this lecture, we'll answer on two questions. In the first question, we'll find out the radius of this circle that is inscribed by triangle ABC. In the second question, we'll find out the area of rectangle ABCD that blocks this circle. So we start with the first question. In the drawing, we have triangle ABC, side BC of triangle ABC equals to 2 units, angle ABC equals to 60 degrees, angle ACB, this angle equals to 75 degrees, and our mission is to find out the radius of this circle that is inscribed by triangle ABC. So we start with the first method. Here we do a construction from point C. We draw perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AB as D. In the next step, we will focus on the green right triangle DBC. So I copy the green triangle in a new page and we'll analyze triangle DBC, the right triangle DBC. Okay. So actually, this is the right triangle DBC that I copied from the original drawing. We know that the sum of the angles in the right triangle DBC is equal to 180 degrees. So which angles we have inside triangle DBC? We have this angle that is a right angle, is equal to 90 degrees, plus this angle that is equal to 60 degrees, plus the size of this angle that we define as angle X. In total, the sum of those three angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. 90 degrees plus 60 degrees is 150 degrees, plus the size of angle X in total must be equal to 180 degrees. Here we subtract 150 degrees from this equation, and we get that the missing angle X equals to 180 degrees minus 150 degrees, it is equal to 30 degrees. So here angle X equals to 30 degrees. Is actually angle DCB, and we'll write down in the original drawing this angle DCB, this angle equals to 30 degrees. So we'll continue to focus on the right triangle, triangle DBC. In the right triangle, triangle DBC, we know that sinus 30 degrees is equal to dB over BC. Okay. Sinus 30 degrees is 1/2, so we substitute sinus 30 degrees by 1/2. It is equal to dB over BC, and BC equals to 2 units, so we substitute BC by 2, and we get that 1/2 equals to dB over 2. We multiply this equation by 2, and we will get that dB is equal to 1 unit. Here dB equals to 1 unit. We'll continue to focus on the right triangle, triangle DBC. In the right triangle, triangle DBC, cosine 30 degrees equals to DC over BC. Okay. Cosine 30 degrees is square root of 3 over 2, and it is equal to DC over BC. BC is 2, so we substitute BC by 2. Here we multiply this equation by 2, and we get that DC equals to square root of 3 units. DC equals to square root of 3 units here. Okay. In the next step, we calculate the size of this angle, angle ACD. Angle ACD equals to the big angle, that is angle ACB, minus this angle, angle DCB. So the big angle ACB equals to 75 degrees, minus this angle that is equal to 30 degrees. 75 degrees minus 30 degrees is 45 degrees. Okay. In the next step, I will copy the right triangle, triangle ADC, in a new page and we'll analyze triangle ADC. Angle ACD equals to 45 degrees. This angle DC equals to square root of 3 units. So this is the right triangle, triangle ADC, that I copied from the original drawing. We know that the sum of the angles in this right triangle, triangle ADC, must be equal to 180 degrees. So we define the missing angle as angle X. So which angles we have inside triangle ADC? We have this angle that is equal to 90 degrees, plus this angle that is equal to 45 degrees, plus the missing angle that is defined as X. In total, the sum of those three angles must be equal to 180 degrees. 90 degrees plus 45 degrees is 135 degrees, plus the size of angle X must be equal in total to 180 degrees. Here we subtract 135 degrees from this equation, and we get that the missing angle X equals to 180 degrees minus 135 degrees. It is equal to 45 degrees. So this angle X equals to 45 degrees. For actually triangle ADC is a right triangle and also an isosceles triangle. So we continue to focus on the right triangle, triangle ADC. In the right triangle, triangle ADC, those two angles are equal to each other, and we have the rule that in front of equal angles in the triangle there are equal sides. So in front of this angle we have side AD, and in front of this angle we have side DC. And according to the rule that I mentioned, those two sides that are located in front of equal angles must be equal to each other. So AD equals to CD, but we have already found out that CD equals to square root of 3 units. And from this equation, square root of 3 equals to CD equals to AD. We derive that AD is also equals to square root of 3 units. AD equals to square root of 3 units. So you can write down in the original drawing that AD equals to square root of 3 units. We continue to focus on the right triangle, triangle ADC. And we'll implement the Pythagoras theorem on this right triangle, triangle ADC. According to the Pythagoras theorem, in the right triangle, triangle ADC, here by PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC, therefore the square of the hypotenuse is AC square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AD square plus DC square. Equation number 1 is the implementation of the Pythagoras theorem in the right triangle, triangle ADC. So here AC square equals to AD square. AD is equal to 3, therefore AD square is equal to 3 squared, that is 3, plus DC square. DC also equals to square root of 3, therefore DC square will be equal to square root of 3, that is 3. So in conclusion, found out that AC square equals to 3 plus 3, that is 6. Here we take a root out of this equation number 1, and we get that AC equals to the square root of 6 units. Now we can write down that AC equals to the square root of 6 units. So actually we found out the lengths of all the sides of triangle ABC. So here we can implement rule number 5 that talks about a radius of a circle that is inscribed by a triangle. So here we have rule number 7. According to rule number 7, we have here this circle with radius r that is inscribed by this triangle ABC, that could be any triangle. According to rule number 7, the radius of this circle is equal to the area of triangle ABC over the semi-perimeter of triangle ABC. And the semi-perimeter of triangle ABC equals to the perimeter of triangle ABC over 2. The length of side AB is A, the length of side BC is C, and the length of side AC is B. Therefore, the perimeter of triangle ABC is A plus B plus C. And if we divide it by 2, we'll get the semi-perimeter of triangle ABC. So we use this formula in order to find out the radius of this circle that is inscribed by triangle ABC. So according to the new formula, the radius of this circle will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. So, what is the area of triangle ABC? The area of triangle ABC is equal to the base of the triangle times the height to the base over 2. Here we will choose the base of triangle ABC as AB. The height to the base will be DC divided by 2. Okay. So we have already found out that AB equals to 1 plus square root of 3 units. DC equals to square root of 3 units. all divided by 2. Here 1 plus square root of 3 units times square root of 3 units over 2 is equal to 2.366 square units. So actually found out that the area of triangle ABC is equal to 2.366 square units. In the next step, we'll find out the semi-perimeter of triangle ABC. The semi-perimeter of triangle ABC equals to the perimeter over 2. That is to say, it will be equal to AB plus AC plus BC over 2. Repeat again, the semi-perimeter of triangle ABC equals to the sum of its sides, the sum of the lengths of its sides over 2. So here AB equals to 1 plus square root of 3 units plus AC it is equal to square root of 6 units plus BC it is equal to 2 all divided by 2. Okay. And in total, this expression is equal to 3.59 units. So in conclusion, we found out that the radius of this circle that is described by triangle ABC, it is equal to the area of triangle ABC over the semi-perimeter of triangle ABC. The area of triangle ABC equals to 2.366 square units over the semi-perimeter of triangle ABC that is equal to 3.59 units. So if we divide the two numbers by each other, we get that the radius is equal to 0.6589 units. Okay. Repeat again, the radius of this circle that is described by triangle ABC equals to 0.6589 units. We finished with the first method. In the next step, I present you how to find out the radius of this circle that is described by triangle ABC according to the second method. In the second method, we define the center of the circle as point O. We will define the point of tendency of tangent DC with this circle as point D. We join points O and D together by a straight line. Point O is the center of the circle. Point D is the point of the circle itself. Therefore, line segment OD is the radius of the circle that we will define as R. OD equals to R. So here we have the radius of this circle that is drawn to the point of tendency. That is to say, it is drawn to point D, that is the point of tendency of tangent BC with this circle. Therefore, this angle will be equal to 90 degrees, and this angle also will be equal to 90 degrees according to rule number 1, that states that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. In the next step, we'll join points O and C together by a straight line. We'll join points O and B together by a straight line. We define the touching the point of tendency of tangent AB with this circle is point E, and we define the point of tendency of tangent AC with this circle as point F. We join points E and O together by a straight line. Point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of the circle that is equal to R, and we have the radius OE that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we join points O and F together by a straight line. Again, point O is the center of the circle. Point F is the point of the circle itself, therefore OF is the radius of the circle that is equal to R. And we have the radius OF that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. In the next step, I present to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. Here we have the common external point, point P. From the common external point, point P, we have two tangents to the circle, tangent PA and tangent PB, and according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. Actually, we can implement rule number 2 in our drawing. We focus on the common external point, point B. From the common external point, point B, we have two tangents to this circle, tangent BD and tangent BE, and according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, BD equals to BE. Likewise, if we focus on the common external point, point C, from point C, we have two tangents to this circle, tangent CD and tangent CF, and according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, CD is equal to CF. Okay, in the next step, we will prove that the green triangle OBD is congruent to the orange triangle, triangle EBO. They congruent to each other according to side rule, but I write it down. Here, the green triangle is actually triangle OBD. In the orange triangle, it's triangle EOB. So why the green triangle is congruent to the orange triangle? First of all, we just right now found out that side BE of the green triangle is equal to side EB of the orange triangle. So you can write down that BD equals to EB according to rule number 2. In addition, DO equals to OE. They are both the radii of the circle that is equal to R. So DO equals to OE equals to R. They are both the radii of the circle, therefore they are equal to each other. Finally, BO is a common side that belongs to both triangles, so side BO equals to itself. It's a common side that belongs to both triangles. So we actually proved that the green triangle is congruent to the orange triangle according to side rule. I write it down. The green triangle OBD, congruent, this is the sign of congruent, to the orange triangle EOB, according to side rule. And from the fact that those two triangles can congruent to each other, we will conclude that those two angles are equal to each other. That is to say, angle OBD in the green triangle is equal to angle OBE in the orange triangle according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides, those two corresponding sides, and those two corresponding angles must be also equal to each other. So if we define one side as alpha, if angle OB equals to alpha, then from this equation angle OBD equals to angle OB equals to alpha, we derive that angle OBD is also equals to alpha. So according to our definition, both those two angles are equal to alpha, and it is given us in the question that the sum of those two angles, that is to say alpha plus alpha, is equal to 60 degrees. Alpha plus alpha is 2 alpha equals to 60 degrees. We will divide the equation by 2 and we will get that alpha equals to 30 degrees. And alpha equals to 30 degrees. So I can write here that this angle alpha equals to 30 degrees. and this angle upright is also equals to 30 degrees. Okay. Likewise, those two triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we conclude that those two angles are equal to each other. That is to say, angle FCO, this angle, is equal to this angle OCD. Okay. Angle FCO equals to angle OCD according to the rule that corresponding sides in congruent triangles are equal to each other. And if we define angle OCD as theta, angle OCD equals to theta, this angle, then from this equation we derive that angle FCO is also equals to theta. So those two angles are both equal to theta, and it is given as the question that the sum of those two angles, that is to say theta plus theta, is equal to 75 degrees. Theta plus theta is 2 theta, 2 theta equals to 75 degrees. We divide this equation by 2, and we get that angle theta equals to 37.5 degrees. So we actually found out that this angle theta equals to 37.5 degrees. And this angle, that is also angle theta, it is also equals to 37.5 degrees. Okay, in the next step, we'll focus on the green triangle OBD. In the green triangle OBD, we know that triangle is 30 degrees is equal to OD over BD. I'll repeat again. In the green triangle, it is very easy to see from the drawing that triangle is 30 degrees equals to OD over BD. OD equals to R, so we substitute OD by R over BD. So in conclusion, we found out that triangle is 30 degrees is equal to R over BD. Repeat again. We found out that triangle is 30 degrees equals to R over BD. Here we will multiply this equation by BD, and then we will divide it by triangle is 30 degrees, and we will get that BD is equal to R over triangle is 30 degrees BD equals to R over triangle is 30 degrees. In the next step, we'll focus on the yellow triangle ODC. In the yellow triangle ODC, It is very easy to see from the drawing that tangents 37.5 degrees is equal to OD over DC. I'll repeat again. In the yellow triangle, triangle ODC, triangle 37.5 degrees equals to OD over DC. Here OD equals to R, so we substitute OD by R. So triangle 37.5 degrees equals to R over DC. So we actually found out that triangle 37.5 degrees equals to R over DC. Here we will multiply this equation by DC and then we divide it by triangle 37.5 degrees. And we get that DC is equal to R over tangents 37.5 degrees. Okay. DC equals to R over tangents 37.5 degrees. So we actually found out the values of BD and DC. And from the drawing, it is very easy to see that BC equals to BD plus DC. BC equals to BD plus DC. Okay. BC equals to BD plus DC. Yeah. BC equals to BD plus DC. So BC equals to BD. We have already found out that BD equals to R over tangents 30 degrees. So we substitute BD by R over tangents 30 degrees, and we have already found out that the DC is equal to R over tangents 37.5 degrees. Therefore, we substitute DC by R over tangents 37.5 degrees. So, in conclusion, we found out that BC equals to R over tangents 30 degrees plus R over tangents 37.5 degrees. Here we take R as a common factor out of those two expressions, and we get that BC is equal to R is a common factor. What is left from R over tangents 30 degrees after we took from it R is a common factor? What is left is actually 1 over tangents 30 degrees. And what is left from R over tangents 37.5 degrees after we took from it R is a common factor? What is left is actually 1 over tangents 37.5 degrees. BC equals to 2 units. According to what is given in the question, so we substitute BC by 2, and it is equal to R. 1 over times 30 degrees is equal to 1.732 plus 1 over times 37.5 degrees equals to 1.303. So I found out that 2 equals to R, and 1.732 units plus 1.303 is equal to 3.035 units. Here we will divide this equation by 3.035 units, and we get that R, the radius that we are looking for, it is equal to 2 over 3.035 units, and it is equal to actually 0.6589 units. So the radius of this circle that is described by triangle ABC equals to 0.6589 units. Okay, so actually we finished with the first question. In the next step, I will present to you the second question, and we'll solve the second question in 2 different methods. In the drawing, we have rectangle ABCD. Inside this rectangle ABCD, we have a circle that is inscribed by the rectangle. Chord PS equals to 6 units. Line segment SQ equals to 5 units, and our mission is to find out the area of this rectangle ABCD. First of all, we know that all the angles inside the rectangle are right angles, so this angle equals to 90 degrees, this angle equals to 90 degrees, this angle equals to 90 degrees, and finally this angle is also equal to 90 degrees. We'll define the length side AB of rectangle ABCD as A. AB equals to A. We'll define the width BC as B. Actually, it is very easy to prove that the width BC is also the diameter of the circle. So I write it down. The diameter of the circle is equal to BC, that is equal to B. We define the center of this circle as O. We join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself. This is exactly the definition of a radius. That is to say, OP is the radius of the circle that we define as R. but we know that the diameter of the circle equals to b. Therefore, the radius must be half of it, that is to say the radius of the circle, that is r, is equal to b over 2. It is half the diameter. Okay, so here we have the radius of P that is drawn to the point of tendency. Therefore, this angle is equal to 90 degrees, and this angle it is also equal to 90 degrees according to rule number 1. Okay. In the next step, I present to you a new rule. This is rule number 4. According to rule number 4, the perpendicular from the center of a circle to a chord bisect the chord. Okay, so here point O is the center of the circle. From the center of this circle, we draw perpendicular on chord CD. And according to rule number 4, the perpendicular OM bisects chord CD. That is to say, CM equals to MD. CM equals to MD according to rule number 4. So you actually can implement rule number 4 in our drawing. From the center of this circle, that is point O, we draw perpendicular on chord SP. So this angle equals to 90 degrees, and this angle is also equals to 90 degrees according to our construction. Okay, we define the touching point of the perpendicular from point O and SP as M, and according to rule number 4, the perpendicular OM from the center of the circle, that is point O, bisects chord SP. That is to say, SM equals to MP according to rule number 4. SM equals to MP. So if we define MP as X, here MP equals to X. From this equation, SM equals to MP equals to X. We derive that SM is also equals to X. SM equals to X, here SM equals to X. So SP equals to SM plus MP, that is to say SP equals to SM, that is X, plus MP, that is X also. So SP equals to 2X. Okay, SP equals to 2X, I'll write it down. But according to what is given us in the question, SP equals to 6 units here. So I can write down that SP equals to 6. And from this equation, 6 equals to SP equals to 2X, we derive that 6 is also equals to 2X. Here we divide this equation by 2. And we'll get that X equals to 6 over 2, that is 3. X equals to 3 units, so we can write down that X equals to 3 units, and then also X equals to 3 units. Okay. In the next step, we define the point of tendency of tangent DC with this circle as F, and we join points O and F together by a straight line. Point O is the center of the circle. Point F is the point of the circle itself, therefore OF is the radius of the circle, that is R. So here we have the radius OF that is drawn to the point of tendency, therefore this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Actually, we created here quadrilateral APCF. In quadrilateral APCF, we have 1, 2, 3 right angles. Again, in this quadrilateral OPFC, we have 1, 2, 3 right angles. Okay? And whenever you have a quadrilateral with 3 right angles, the fourth angle must be also a right angle. So this is the fourth angle that must be also a right angle in order to complete the sum of the angles inside quadrilateral OPCF 280 degrees. This angle must be also equal to 90 degrees. Okay. In the next step, from point Q, this point Q, we'll draw perpendicular on BC. Repeat again, from point Q, we'll draw perpendicular on BC. Here from point Q, we go perpendicular on BC. So this angle equals to 90 degrees, and this angle it is also equal to 90 degrees according to our construction. We will define the touching point of the perpendicular from point Q and BC as H, so here we define the intersection point of the perpendicular QH and the radius QF as T. So by drawing this perpendicular QH, we created here quadrilateral QPTH. We have here quadrilateral QPTH. Inside quadrilateral QPTH, we have 1, 2, 3 right angles. Okay, 1, 2, 3 right angles. So any quadrilateral that has 3 right angles, the fourth angle must be also a right angle. So this is the fourth angle that must be a right angle. So inside quadrilateral QPTH, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral QPTH as a rectangle. I repeat again. Quadrilateral QPTH is a rectangle because it has 4 right angles. And we also know that the opposite sides of a rectangle are parallel to each other. So the opposite sides of rectangle QPTH are parallel to each other, or PTH. The opposite sides of rectangle OPTH are parallel to each other. That is to say, side OP is parallel to side TH. OP is parallel to TH. Side OP is parallel to side TH. But what is actually the definition of side TH of rectangle OPTH? TH is part of perpendicular QH. Okay, TH is part of perpendicular QH, and QH as a perpendicular, it is absolutely a straight line. So you can write down that QH is a straight line because it is a perpendicular. QH is a straight line. QH is a perpendicular. It is absolutely a straight line. And we know that TH is part of the straight line QH. TH is part of the straight line QH, and TH is parallel to OP. So you can say that part of the straight line QH is parallel to OP. So if part of the straight line QH is parallel to OP, it means that the straight line QH must be also parallel to OP. I write it down. The straight line QH must be also parallel to OP. Why? Because if part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Okay? In the next step, I will present to you rule number 9. According to rule number 9, alternating angles between parallel lines are equal to each other. Here, line A is parallel to line B. Those two pink angles are defined as alternating angles, and they are located between the parallel lines A and B. Therefore, they are equal to each other. Okay, those two alternating angles are equal to each other because they are located between the parallel lines A and B. We can implement rule number 9 in our drawing. Because in our drawing, we have the parallel lines OP and QA. Those two angles are defined as alternating angles, and they are located between the parallel lines OP and QH, therefore they are equal to each other. Okay, so here, this angle OPQ, is equal to this angle, that is actually angle HQP. Repeat again. The alternating angles OPQ and HQP are equal to each other according to rule number 9, because they are located between the parallel lines QH and HP. So if we define angle QP and OPQ, if we define angle HQP as theta, here angle HQP equals to theta according to our definition, then from this equation angle OPQ equals to angle HQP equals to theta, we derive that angle OPQ is also equals to theta. Okay, here this angle OPQ is equal to theta. Okay, you can write here also that this angle equals to theta. In the next step, we'll focus on quadrilateral QHCD. In this quadrilateral, we have 1, 2, 3 right angles. Again, in quadrilateral QHDC, we have 1, 2, 3 right angles. And if a quadrilateral has 3 right angles, the fourth angle must be also equal to 90 degrees. So this angle is also equal to 90 degrees. So actually inside quadrilateral QHDC, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral QHDC as a rectangle. Quadrilateral QHDC is a rectangle and we know that the opposite sides of a rectangle are equal to each other. That is to say, QH equals to DC. QH equals to DC. So inside rectangle QHDC, we know that its opposite sides are equal to each other. That is to say, QH equals to DC. But we know that ABCD is a rectangle and the opposite sides of rectangle ABCD must be equal to each other. That is to say, DC is equal to AB. In rectangle ABCD, side DC equals to side AB. And from this equation, QH equals to DC equals to AB, we will derive that QH is equal to AB. QH is equal to AB. But according to our definition, AB equals to A. So I can write down that AB equals to A. And from this equation, QH equals to AB equals to A, we will derive that QH is also equals to A. Okay, QH is also equals to A. have found out that QH is equal to A In the next step, we'll focus on the right green triangle, triangle OMP. So I will copy triangle OMP in a new page and we will analyze the right green triangle, triangle OMP. MP equals to X, that is equal to 3 units. The hypotenuse OP equals to B over 2, it is the radius of the circle. Angle OPM is equal to theta. So actually, this is the right triangle, triangle OMP that I copied from the original drawing. In the right triangle, triangle OMP, it is very easy to see from the drawing that cosine theta equals to MP over OP. I'll write it down. Cosine theta equals to MP over OT. MP over OP. Here. Cosine theta is equal to MP over OP. MP equals to 3, so we substitute MP by 3. OP equals to B over 2, we substitute OP by B over 2. Here we have 3 over B over 2. We will move to the 2 to the numerator. 2 times 3 is 6. We will move B to the denominator. So in conclusion, we found out that cosine theta, according to equation number 1, is equal to 6 over B. Okay. In the next step, we will focus on the right big triangle, PQH. On the right big triangle, PQH. It is very easy to see from the drawing that cosine theta equals to QH over QP. I'll repeat again. On the right big triangle QPH, cosine theta equals to QH over QP. Okay, so what is the value of QH? The value of QH, according to what we have already found out, is equal to A. So we substitute QH by A. And what is the value of QP? The value of QP, it is very easy to see from the drawing that QP equals to 5 plus 6. Again, QP equals to 5 plus 6, that is 11, so we substitute QP by 11. So in conclusion, we found out that according to equation number 2, cosine theta equals to A over 11. So here we actually have two different expressions for cosine theta in equation number 1 and equation number 2. Therefore, we will create equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. Okay. Cosine theta according to equation number 1 is equal to 6 over b, and it must be equal to cosine theta according to equation number 2 that is equal to a over 11. So in conclusion, we found out that according to equation number 3, 6 over b is equal to a over 11. Okay. Here we cross multiply this equation number 3, and we get that according to equation number 3, a times b equals to 66. Found out that according to equation number 3, a times b equals to 66. So, and what is the area of triangle ABC? The area of triangle ABC equals to the length of triangle ABC times the width. So I write it down. The area of triangle ABC, the area of rectangle ABC actually. Of course, the area of rectangle ABC is equal to the length of the rectangle times the width. Okay. The length is equal to AB, the width is BC. AB times BC is the area of triangle ABC, D. AB times BC is the area of rectangle ABC, D. According to our definition, AB equals to A and BC equals to B. So in conclusion, we found out that the area of rectangle ABCD is equal to AB, but we just right now found out that according to equation number 3, A times B equals to 66. So we can write here that AB equals to 66. And we, in conclusion, we found out that the area of rectangle ABCD is equals to 66 square units. Okay. So we finished with the first method. In the next step, I will present to you how to find out the area of this rectangle ABCD according to the second method. We know that all the angles inside the rectangle are right angles, so all those angles are right angles. As we did in the first method, we define the length AB as A. AB equals to A according to our definition. We define the width BC as B. somebody explained in the first method, the diameter of this circle is equal to BC, that is B. It is very easy to prove it, but we will not do it. Okay. We define the center of the circle as O. We join points P and O together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of this circle that we will define as R. If the radius OP equals to R and the diameter is equal to B, then the radius must be equal to half of it, that is to say R is equal to B over 2. Here, according to the first method, we have already found out that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. In the next step, we will extend the radius PO until it intersects with side AD of rectangle ABCD. We define the intersection point of the extended radius PO and AD as L. So here, by this construction, we actually created here quadrilateral ABLP. Inside quadrilateral ABLP, we have 1, 2, 3 right angles. Therefore, the fourth angle, this angle, must be also equal to 90 degrees. Inside quadrilateral ABLP, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate quadrilateral ABLP as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to LP. AB equals to LP, but AB equals to A, and LP equals to AB. Therefore, LP must be also equal to A. We define the touching point of the extended radius PO and the circle as T. We have here chord TP. And chord TP passes through the center of the circle, that is point O. Any chord that passes through the center of the circle must be the diameter of the circle. So TP is the diameter of the circle. Why? Because it is a chord that passes through the center of the circle, and any chord that passes through the center of the circle is the diameter of the circle. So TP is the diameter of the circle, and we have already found out that the diameter of the circle is equal to B. We will join points C and S together by a straight line. By joining points C and S, we created here peripheral angle as PST. This peripheral angle PST rests on TP, that is the diameter of the circle, and we actually have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of the circle must be equal to 90 degrees. Here we have peripheral angle AB that rests on AB, that is the diameter of the circle, therefore it is equal to 90 degrees. We can implement all number 5 in our drawing. Why? Because in our drawing we have peripheral angle PST that rests on TP, that is the diameter of the circle. Therefore, according to rule number 5, peripheral angle PST is equal to 90 degrees. Okay, we define angle TPS as theta. So inside the right triangle TSP, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. If we focus on the big right triangle LQP, this angle equals to theta, this angle here. What is the size of this angle? If we focus on quadrangle LPDC, in quadrangle LPDC, we have 1, 2, 3 right angles. And any quadrangle that has 3 right angles, its fourth angle must be also equal to 90 degrees. So here inside, the fourth angle, that's angle DLP, must be equal to 90 degrees. So we continue to focus on the right triangle LQP. Inside triangle LQP, this angle equals to theta, this angle equals to 90 degrees. Therefore, the third angle must be equal to 90 degrees minus theta, as I already explained about this angle, for the same reason exactly. So here, in the next step, we'll prove that the green right triangle TSP, is similar to the big right triangle LQP. So I write it down. We prove that the big right triangle LQP, this triangle, is similar to the small green right triangle PST. So why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So here, this angle, it is angle LQP. And it is equal to this angle, that is actually angle STP. Repeat again. Angle LQP equals to angle STP. They are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So here angle QLP is equal to this angle, that is actually angle TSP. Repeat again. Angle QLP equals to angle TSP. They are both equal to 90 degrees, therefore they are equal to each other. And finally, this angle theta, is a common angle that belongs to both angles, so angle theta equals to itself. That is to say, angle LPQ, that is one name of angle theta, is equal to angle TPS, that is the other name for the same angle, angle theta, TPS. So here, angle LQP, that is angle theta, is equal to angle TSP, that is also angle theta. So angle theta equals to itself, it's a common angle that belongs to both triangles. So we actually proved that the big triangle LQP is similar to the small green triangle TSP. According to angle similarity rule. And from the fact that those two triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that side LP in the big right triangle over side SP in the small green right triangle is equal to side QP in the big right triangle over side TP in the small green right triangle. Repeat again, we conclude that LP over SP equals to QP over TP. Okay. LP equals to A. According to what we already found out, we'll substitute LP by A over SP equals to X according to what is given as the question. So we substitute SP by 6, and it is equal to QP. It is very easy to see from the drawing that QP equals to 5 plus 6. QP equals to 5 plus 6, that is 11. So we substitute QP by 11 over TP. TP is the diameter of the circle, that is equal to B. So we substitute TP by B. So in conclusion, we found out that according to equation number 1, A over B equals to 11 over A over 6 equals to 11 over B. Here we cross multiply this equation number 1, and we get that according to equation number 1, A times B equals to 6 times 11 is 66. So AB equals to 66 according to equation number 1. And what is the area of rectangle ABCD? The area of rectangle ABCD is equal to the length of the rectangle, that is AB, times the width, that is BC. The length is equal to AB according to A according to our definition. The width BC is B according to our definition. So in conclusion, we found out that the area of triangle ABCD is A times B, but we just right now found out that A times B equals to 66. So we can write here that AB equals to 66. So in conclusion, we found out that the area of rectangle ABCD is equal to 66 square units. Okay. we finished with the second method and the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the drawing, we have triangle ABC, angle ABC equals to 60 degrees, angle ACB equals to 75 degrees, side BC equals to 2 units. Inside triangle ABC, we have a circle, or this circle is inscribed by triangle ABC, and our mission is to find out the radius of this circle that is inscribed by triangle ABC. We started with the first method. In the first method, from point C, we drew perpendicular on AB. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB is D. Then I copied the green triangle DBC and we analyzed triangle DBC. This is the right green triangle DBC that I copied from the original drawing. And here we know that the sum of the angles in triangle DBC must be equal to 180 degrees. So which angles we have inside triangle DBC? This angle equals to 90 degrees, this angle equals to 60 degrees, plus this angle, that is the missing angle, is equal to x. In total, the sum of those three angles must be equal to 180 degrees. So here 90 degrees plus 60 degrees is 150 degrees, and 150 degrees plus x must be equal to 180 degrees. We subtracted 150 degrees from this equation and found out that the missing angle x equals to 180 degrees minus 150 degrees, it is 30 degrees. So here x equals to 30 degrees. We continue to focus on the right triangle DBC, the right triangle DBC. Here it is very easy to see from the domain that sin 30 degrees equals to dB over BC. dB over BC. Sin 30 degrees is 1/2, so substitute sin 30 degrees by 1/2. And it is equal to dB over BC, but BC is 2, so we substitute BC by 2. Here we multiply this equation by 2 and found out that BD equals to 1 unit. Here, BD equals to 1 unit. We continue to focus on the right triangle DBC. In the right triangle DBC, cosine 30 degrees equals to DC over BC. Again, cosine 30 degrees equals to DC over BC. So cosine 30 degrees is equal to 3 over 2. And it is equal to DC over BC. BC equals to 2. So in conclusion, we found out that square root of 3 over 2 equals to DC over 2. Multiply this equation by 2 and found out that DC equals to square root of 3 units. Here, DC equals to the square root of 3 units. Then we calculated the size of this angle ACD. The size of this angle ACD equals to the size of the big angle ACB minus the size of the small angle DCB. That is to say, it is equal to the size of the big angle is 75 degrees, the size of the small angle is 30 degrees. 35 degrees minus 30 degrees, it is 45 degrees. Then I copied the right triangle ACD in the new page and analyze triangle ACD. So this is the right triangle ADC that I copied from the original drawing, and the sum of the angles inside triangle ADC must be equal to 180 degrees. So which angles we have inside triangle ADC? We have this angle that is equal to 90 degrees, plus this angle that is equal to 45 degrees, plus the missing angle that we define as x. In total, the sum of those three angles must be equal to 180 degrees. 90 degrees plus 45 degrees is 135 degrees, so 135 degrees plus x equals to 180 degrees. We subtracted 135 degrees from this equation and found out that the missing angle x equals to 180 degrees minus 45 degrees. It is 180 80 degrees minus 135 degrees, it is equal to 45 degrees. So the missing angle, this angle equals to 45 degrees. We continue to focus on the right triangle ADC. In the right triangle ADC, those two angles are equal to each other, and we know that in front of equal angles in the triangle there are equal sides. In front of this angle, we have side DC. In front of this angle, we have side AD, and those two sides that are located in front of equal angles must be equal to each other. That is to say, AD equals to CD. But we have already found out that CD equals to square root of 3 units. And from this equation, square root of 3 equals to CD equals to AD, we derive that AD is also equals to square root of 3 units. We continue to focus on the right triangle ADC. We implemented the Pythagoras theorem on the right triangle ADC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC squared equals to AD squared plus DC squared. AC squared equals to AD squared. AD is square root of 3, therefore AD squared is square root of 3 squared, that is 3, plus DC squared. DC is square root of 3, so therefore DC squared is square root of 3 squared, that is also 3. So in conclusion, we found out that AC squared equals to 3 plus 3, that is 6. We took out of this equation number 1, and we found out that AC equals to the square root of 6 units. Here, AC equals to the square root of 6 units, so I actually found out the lengths of all the sides of triangle ABC. And in the next step, we use a special formula for the area of for the radius of any circle that is inscribed by a triangle. The radius of the circle that is inscribed by a triangle will be equal to the area of the triangle that blocks the circle over the semi-perimeter of the triangle. The semi-perimeter of any triangle is equal to the perimeter over 2. So first of all, we found out the area. In order to find out the radius of our circle, we have to find out the area of triangle ABC that blocks the circle. The area of triangle ABC equals to the base of the triangle that is AB times the height to the base that is CD. The base is AB, the height is CD over 2. AB equals to 1 plus square root of 3, CD equals to square root of 3 over 2. This expression equals to 2.366, so the area of triangle ABC equals to 2.366 per units. Then the semi-perimeter of triangle ABC equals to the sum of its side lengths over 2. The sum of its side lengths is AB plus AC plus BC over 2. AB is 1 plus square root of 3 units, AC is square root of 6 units, and BC is 2. All divided by 2 will give us the semi-perimeter. The value of this expression is 3.59. So the semi-perimeter of triangle ABC is 3.59 units, and the radius, according to the new formula of the circle that is described by triangle ABC, will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. We found out that the area of triangle ABC is equal to 2.366 per unit, and the semi-perimeter of triangle ABC is equal to 3.59 units. Okay, so 2.366 over 3.59 is equal to 0.6589 units. The radius of this circle that is described by triangle ABC equals to 0.6589 units. We finished with the first method, then I presented to you the second method. In the second method, we define the center of this circle as point O. Here, all the angles here, they are right angles according to rule number 1. Here, the radii are drawn to the point of tendency, therefore according to rule number 1, all those angles are right angles. Then I presented to you rule number 2, according to rule number 2, the lengths of two tangents from a common external point to a circle are equal. From the common external point P, we have tangent PA and tangent PB, and according to rule number 2, the lengths of two tangents are equal to each other, that is to say PA equals to PB. Okay. If you focus on the common external point P, from the common external point B, we have two tangents to the circle, tangent BE and tangent BD, and according to rule number 2, the lengths of those two tangents are equal to each other, that is to say BE equals to BD. Likewise, if you focus on the common external point C, from the common external point C, we have two tangents to this circle, tangent CD and tangent CF, and according to rule number 2, the lengths of those two tangents are equal to each other, that is to say CD equals to CF. Then we prove that the green triangle is congruent to the orange triangle according to side rule. I'll explain why those two triangles congruent to each other. First of all, those two sides are equal to each other according to rule number 2. In addition, those two sides, they are both the radii of the circle, therefore they are equal to each other. And finally, OB is a common side that belongs to both triangles, so OB equals to itself. So those two triangles can go into each other according to side rule, therefore those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So we know that if one angle is equal to alpha, then the other angle must be also equal to alpha. And the sum of those two angles is alpha plus alpha is 2 alpha, and 2 alpha equals to 60 degrees. We divided the equation by 2 and found out that alpha equals to 30 degrees. So each angle equals to 30 degrees. Then we focus on the, actually here, those two triangles also can go into each other according to side rule. Therefore, those two angles must be also equal to each other. So if one angle is equal to theta, then the other angle must be also equal to theta. So theta plus theta is 75 degrees according to what is given as the equation. We divided the equation by 2 and found out that angle theta equals to 37.5 degrees. Okay, then we focused on the green triangle ODB. In the green triangle OBD, triangles 30 degrees equals to OD over BD. Again, triangles 30 degrees equals to OD over BD. OD equals to R. So if we found out that triangles 30 degrees equals to R over BD, we multiplied this equation by BD and then we divided by triangles 30 degrees and found out that BD equals to R over triangles 30 degrees. Then we focused on the yellow right triangle ODC. The yellow right triangle ODC, triangles 37.5 degrees equals to OD over DC. Triangles 37.5 degrees equals to OD over DC. OD equals to R, therefore triangles 37.5 degrees, R equals to R over DC. We multiply this equation by DC and then we divide it by triangles 37.5 degrees and found out that DC equals to R over triangles 37.5 degrees. So we have the values of BD and DC, and from the drawing it is very easy to see that the value of BC equals to BD plus DC. Okay, here BC equals to BD plus DC. BD equals to R over triangles 30 degrees, DC equals to R over triangles 37.5 degrees. We took R as a common factor and we got that BC equals to R times 1 over triangles 30 degrees plus 1 over triangles 37.5 degrees. 1 over triangles 30 degrees is 1.372 and 1 over triangles 37.5 degrees is 1.303. And the sum of those two numbers is 3.035. So 2 equals to R times 3.035. We divided this equation by 3.035 and found out that r equals to 2 over 3.035. That is actually equals to 0.6589 units. So the radius of this circle that is described by triangle ABC equals to 0.6589 units. We finished with the first question. Then I presented to you the second question, and we solved the second question in two different methods. So in the drawing, we have rectangle ABCD. Inside the rectangle, we have a circle that is inscribed, chord SP equals to 6 units, line segment QS equals to 5 units. And our mission is to find out the area of this rectangle ABCD. So we define the center of the circle as point O. We join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP equals to the radius of the circle that we defined as R. We define side AB as A and side BC as B. The diameter of the circle is equal to B. So if the diameter is B, then the radius must be equal to B over 2. We join points O and F together by a straight line. Point O is the center of the circle. Point F is the point of the circle itself. Therefore, OF is the radius of this circle that is equal to R. The radius here is drawn to the point of tendency. Therefore, this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. Inside quadrilateral OP and FC, we have 1, 2, 3 right angles, therefore the fourth angle, this angle must be also equal to 90 degrees. Then I presented to rule number 4 that if you draw from the center of the circle that is O perpendicular to chord SP, then that perpendicular OM bisects chord SP, that is to say SM equals to MP. So SM equals to MP. So if MP equals to X, then from this equation SM equals to MP equals to X, we derive that SM is also equals to X. So here you can see that X plus X equals to SP. X plus X equals to SP, but SP equals to 6. According to what is given as equation, and from this equation 6 equals to SP equals to 2X. We will derive that 6 equals to 2X. We divided this equation by 2 and found out that X equals to 3 units. Here X equals to 3 units, X equals to 3 units. Okay, then from point Q, we draw perpendicular on BC, that this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and BC as H. And here, actually, we created here quadrilateral OPLH. Inside quadrilateral OPLH, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Inside quadrilateral OPLH, we have 4 right angles. Therefore, quadrilateral OPLH is a rectangle. The opposite sides of a rectangle are parallel to each other. That is to say, OP is parallel to LH. Actually, it is point T. This point is point T. Therefore, OP is parallel to TH. OP is parallel to TH according to the rule that the opposite sides of a rectangle are parallel to each other. But TH is part of QH. And QH is a perpendicular, it is absolutely a straight line. So if part of the straight line QH is parallel to OP, it means that the straight line itself QH must be also parallel to OP, because if a part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Therefore, QH is parallel to OP. QH is parallel to OP, and we have rule number 9, that alternating angles between parallel lines are equal to each other. Those two angles are defined as alternating angles and are located between the parallel lines OP and QH, therefore they are equal to each other. That is to say, angle OPQ equals to angle HQP. So if one angle is equal to theta, then the other angle must be also equal to theta, because those two angles are equal to each other. So both those two angles are equal to theta. Then we focus on quadrilateral QHCD. Inside quadrilateral QHCD we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So quadrilateral QHDC that has 4 right angles is a left angle, and the opposite sides of left angle are equal to each other. That is to say, QH equals to DC. But DC is equal to AB because ABCD is a left angle. Okay, and from this equation QH equals to DC equals to AB, we will derive that QH is equal to AB. QH equals to AB, but according to our definition, AB equals to A. So from this equation QH equals to AB equals to A, we will derive that QH is also equals to A. Here, QH equals to A. Then we implemented here, I copied the right triangle OPM in this new page. In the right triangle OMP, cosine theta equals to 3 over B over 2, that is 6 over B. So according to equation number 1, cosine theta equals to 6 over B. Then we focused on the big right triangle OPH, QPH. Here cosine theta equals to QH over QP. Cosine theta equals to QH over QP. QH equals to A, and QP equals to 5 plus 6, that is 11. So in conclusion, according to equation number 2, cosine theta equals to A over 11. Then we added equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. Cosine theta according to equation number 1 is equal to 6 over B. That must be equal to cosine theta according to equation number 2. That is equal to A over 11. So according to equation number 3, we found out that 6 over B equals to A over 11. We cross multiply this equation and we found out that A times B equals to 66. And the area of rectangle ABCD equals to its length times its width. The length is AB, the width is BC, AB equals to A and BC equals to B according to our definition. And we just right now found out that AB equals to 66. So in conclusion, we found out that the area of rectangle ABCD equals to 66 square units. Then I presented to you how to find out the area of this rectangle ABCD according to the second method. In the second method, we define AB as A, BC as B. BC is also the diameter of the circle. We join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle that is equal to R. If the diameter is equal to B, then the radius must be equal to B over 2. We extended the straight line PO until it intersects with side AD of rectangle ABCD. So here we have quadrilateral ABPL. Inside quadrilateral ABPL we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So inside quadrilateral ABPL, we have 4 right angles, therefore quadrilateral ABPL is a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to PL. But AB equals to A, therefore PL is also equal to A. Likewise, in quadrilateral LPDC, we have 1, 2, 3 right angles, therefore the fourth angle, this angle must be also equal to 90 degrees. Then we join points T and S together by straight line. In this way, we created peripheral angle LSP. PT is the diameter of the circle because chord PT passes through the center of the circle, and any chord that passes through the center of the circle must be the diameter of the circle. And here, peripheral angle TSP rests on TP, that is the diameter of the circle, and any peripheral angle that rests on the diameter of the circle must be equal to 90 degrees according to rule number 5. We define this angle as theta. So this angle equals to 90 degrees, this angle equals to 90 degrees, this angle equals to theta, therefore this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in triangle TSP to 180 degrees. This angle must be equal to 90 degrees minus theta. Likewise, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. Then we prove that the green right triangle is similar to the big right triangle LPQ. Why those two triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. And finally, this angle theta is a common angle that belongs to both triangles, so this angle equals to itself. So we actually proved that the big triangle NQP is similar to the small green triangle TSP according to angle similarity rule. And from that we can derive that LP over SP equals to QP over TP. Here LP equals to A, SP equals to 6, QP equals to 5 plus 6, that is 11, and TP is the diameter of the circle, that is equal to B. So in conclusion, found out that A over B equals to 11, A over 6 equals to 11 over B. We first multiplied the equation number 1 and found out that AB equals to 66. And thereafter triangle ABCD equals to the length of the triangle, that is AB, times the width, that is BC. So AB times BC is thereafter triangle ABCD. AB equals to A and BC equals to B according to our definition. So in conclusion, we found out that thereafter triangle ABCD equals to AB. And we just right now found out that AB equals to 66. So therefore, thereafter triangle ABCD equals to 66 square units. So in both methods, we found out that thereafter triangle rectangle ABCD equals to 66 square units. Okay, thank you very much.